Just a correction, I missed the L over here. So this is supposed to be a hydroxyl group. Okay, so this is another problem where I am asking to draw the structural isomers of certain molecular formula, and I'm specifying that I need an aldehyde that has this molecular formula. Now, the first thing that you would do, you should write the general formula of the aldehyde. This is the general formula of the aldehyde. For the ketone, the general formula of the ketone is RC double bond OR. You have two R chains surrounding the carbonyl. And then for the carboxylic acid, it's an RC double bond O. I always start writing the general formula and then I make it specific based on the molecular formula. And then D, they need an ester, and this is how the ester looks like. So you would know that you have a CO, C double bond O. This is what makes the ester. Okay, so this is what makes the ester. This is what makes the ketone. This is what makes the aldehyde, and this is what makes the carboxylic acid. And then you go ahead and you look at your molecular formula. I know that the aldehyde is at the end. I have 4 carbons, so go ahead and put the 4 carbons over here. So you have the 4 carbons. The last carbon is the carbonyl. I don't have a room to add one more carbon. So the last carbon is the carbonyl, and I have here a hydrogen. So the whole thing here, see, all of that is the R. So all of this is the R group. This is the R group here. So you have RC double bond OH. For the for the ketone, same molecular formula. So so what we want here is the so I need still 4 carbons. Here you go. Now I need the carbonyl. The carbonyl can either be here or it can be here. It really doesn't matter because both structures will be the same. So I'm going to put the carbonyl over there. This is my first R. This is my second R. So you have 2 R's over here. See, this is your first R. And then that is your second R. And then you have the carbonyl in the middle. Whether you wrote it like this or you wrote it like this, these two are the same. So you have a CH3 here, I have a CH3 here. I have a CH2CH3 here, I have a CH2CH3 here. So these two are the same. So these two are the same ketones. Now for the acid is a functional group at the end of the chain, like the aldehyde. So I have 4 carbons over here. This is 1, 2, 3, and 4. The last carbon, which is this one over here, is the one that is connected to the OH. So this is going to be my R. So all of that is basically the R. So this is going to be the ROH. I'm sorry, RC double bond OH. And then the last one here, I have my 4 carbons again. So draw your 4 carbons. Okay, now notice here what I have. I have an oxygen. So you're going to put the oxygen somewhere. So I'm going to draw my 3 carbons, not 4, because I have a total of 4 that are divided between these two R's. So I'm going to put the 3 on one end. And then I'm gonna put basically a double bond O over here. This is gonna be my 4. Let me put the eraser in there. Okay. So that is gonna be an O, and then here you go. So notice how many carbons did I use here? 1, 2, 3, and then I have another one over here. So this is basically my 4. Let's go ahead and count the hydrogens. Make sure in each one of those the hydrogens is equivalent to whatever you have in your molecular formula. So I need 8 hydrogens. This is the 3 hydrogens over here. 4, 5, 6, 7, and 8. Okay, so I can do it this way, or I can have a I can do it like this. I can have a an oxygen here, okay, and then a double bond O. It's gonna be the, okay, so here you go. I can do it like that. 1, 2, 3, and 4. So I can have next to the carbonyl a chain of 2 carbons, or I can have next to the carbonyl a chain of 1 carbon. Let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, and 8. So I can have next to the oxygen a CH3, or next to the oxygen a CH2CH3. Any one of those is the ester, because I still have my carbon double bond O. This is basically the ester functional group. I still have it in both of them. Okay. So basically the functional group determines everything from the type of bonding, to the molecular shape, to the strength of the intermolecular force, to the physical properties, to the way that you name the organic compound, to the chemical reactivity of the compound. So see why the functional groups are very important. Now this is just a review of intermolecular forces. Intermolecular forces, we've explained it in Gen Chem 2. We explained it in details in Gen Chem 2, so this is just a revision. Intermolecular forces, these are interactions. So intermolecular forces, I normally abbreviate them as IMF. So if you see that, this is intermolecular forces. These are interactions, they exist between the molecules. And the type of the functional group basically determines what type and the strength of intermolecular forces you have within the molecule. You do have 2 types of compounds, ionic and covalent, and both they have intermolecular forces with different strength. So let's start with the ionic. The ionic compounds that have an ionic bond, like for example NaCl. We said that the ionic bond is formed between group 1, 2, 3 and groups 5, 6, and 7. So this is an example of sodium chloride. It's a salt that is formed from sodium, which is in a group 1, and the chlorine, which is in a group 7. You can see that you have an ion-ion interaction. So the type of force between them is an electrostatic interaction. That electrostatic interaction is very, very strong. So ion-ion interaction, this is the strongest type of intermolecular forces. These charges, basically, they are held together by electrostatic interactions. They are very strong, and they are stronger than any of the intermolecular forces that are present in covalent bonds. Remember, this is an ionic bond. It is not a covalent bond. Now, with respect to the covalent bonds, there are 3 types of intermolecular forces. The weakest is the van der Waal. We call it London forces. These are the weakest types of intermolecular forces. And then you have the dipole-dipole interaction. This happens whenever you have a polar molecule, or you have a section of the molecule which is polar, like a carbonyl, like an OH. If it doesn't have to be the whole molecule to be polar, it's just a section of it that has a polar bond will exhibit or will form a dipole-dipole interaction. And then we have the hydrogen bonding. This is the strongest type of intermolecular forces. Let's start with the weakest. The weakest are London forces. Those, they exist in every single structure that has carbon. They are very weak. They are present in nonpolar compounds, and not just nonpolar compounds. They are basically the result of an electronic cloud. So any compound, whether it is polar or nonpolar, will have a van der Waal force because it will have an electronic cloud around it. and that electronic cloud will result in a temporary dipole. Now, what do I mean by dipole? Dipole means a change in the charge. And normally dipoles are caused whenever you have an electronic cloud. So if you have an electronic cloud, electrons try to arrange in a certain way so that so that they bring the stability to the molecule. One end of the dipole is going to be partial positive, the other end is going to be partial negative. Here I have an example of two CH4 molecules that are present next to each other. Now CH4 is nonpolar. This is an sp3 hybridized carbon. This is nonpolar. So if I have two nonpolar molecules here in this example present next to each other, I know both of them are nonpolar, and however there is an electronic cloud around each one of them. The electronic cloud is the result of the difference, the slight difference in the electronegativity. Carbon is slightly more electronegative than hydrogen, so that will introduce basically that temporary dipole in there. So if you place these two CH4s next to each other, one end of the dipole will be partial positive. That will attract the partial negative dipole of the second molecule of the CH4. If you have a partial positive dipole here, then same charges normally repel each other. So this is basically what van der Waals forces are. Normally all compounds, they exhibit van der Waals forces, not just nonpolar compounds. All compounds that have carbons and hydrogens, they exhibit or they have van der Waals forces. The rule is the larger the surface area of the molecule, the larger the attractive forces between the molecule, because see, this is the attractive forces over here. So as the molecule becomes longer, as the charges around or across the molecule in here will occupy more space, so the stronger will be the intermolecular forces in this case, due to larger surface area and larger attractive forces between the molecules. Compared to a compact molecule here, see, I am giving an example of a 5-carbon compound. This 5-carbon compound here, this is basically called neopentane. Neopentane is a branched 5-carbon compound. This is an N chain. This is pentane. Again, it's 5 carbons, but it is an N chain over here where the charge is spread over a larger surface area. So this is gonna make the intermolecular forces, the van der Waals forces in this case, is gonna be stronger when the molecule is larger, and you have here larger attractive forces between the two molecules. Another function that affects the van der Waals forces is the polarizability. Now, when we say polarizability, we mean electronegative elements, and the effect of the electronic cloud on the size of the electronic with respect to the size of the electronegative element. So polarizability, it's a term that we use for electronegative elements, so fluorine, chlorine, bromine, and iodine. It's the same idea. So polarizability, it's the measure of how the electronic cloud around the atom, not just any atom, electronegative halogens or atoms, responds to the changes in the environment. Normally, if you have larger atoms, iodine, we said that the size increases as you go down the periodic table. So iodine are bigger in size than fluorine. So larger atoms like iodine in here, normally they have more loosely held valence electrons. And the reason why they have more loosely held valence electrons, because their valence electrons, they are far away from the nucleus, because the charge or the size of the atom is bigger. So the valence electrons are farther away from the nucleus. So the valence electrons are loosely held. So when they are loosely held, they are now more polarizable than the small atoms like a fluorine, which has its valence electrons closer to the nucleus. And this is what the idea for polarizability is. Polarizability is the electronic cloud around the molecule, and not just any molecule. It's just it's the electronegative element, and how this electronic cloud basically is. With respect to the nucleus of the atom, is it closer or is it far away from the nucleus of the atom? The smaller the atom is, the less polarizable the atom is, and the weaker the forces of attraction. As you can see, the molecule here, the fluorine, is smaller in size, so the electronic cloud around the fluorine occupies a smaller surface area compared to the electronic cloud around the iodine, which occupies a greater surface area. So the larger the atom is, the more polarizable it is, and the stronger the forces of attraction. The second type of intermolecular forces, now this one is stronger than the van der Waals forces, and that is due. It's a dipole-dipole interaction. These are attractive forces, and these attractive forces are between dipoles. So here I have three molecules of acetone next to each other. See, if I want to put them next to each other, this is how they are arranged. You have your direction of polarization. This is partial positive, this is partial negative. So that is going to force the second molecule to have its partial positive end on this side, so that these two charges, partial charges, won't repel each other, they will attract each other. This is called a dipole. A dipole is a polar section of the molecule. I know that the CH3 here and the CH3 here, the CC, this is nonpolar, this is nonpolar, this is nonpolar, but your polar section here is the carbon double bond O. So this is basically your dipole in this case, and these are the dipole-dipole interactions. These interactions, they are caused by permanent dipoles. They are stronger than the van der Waals forces. And then the last thing you have is the hydrogen bonding. By definition, this is an imaginary type of interaction, and hydrogen bonding happens between a hydrogen, because it's called hydrogen. Hydrogen is a must. The hydrogen needs to be connected to, so hydrogen has to be connected to either an oxygen or a nitrogen or a fluorine. Either one of these elements, you don't have any other choice. So hydrogen has to be connected to any of those elements in here. And to make hydrogen bonding, it needs to bond with an electronegative element. Now this electronegative element doesn't matter what it is connected to, but it has to be an oxygen, a nitrogen, or a fluorine. So this is why water does hydrogen bonding. Again, hydrogen bonding is not an actual bond. It is basically an interaction between a hydrogen that is connected to an electronegative element and an electronegative element in there. Hydrogen bonding is the strongest type of intermolecular forces. So as the polarity of the organic molecule increases, so does the strength of its intermolecular forces. Van der Waals forces, we can see over here. Van der Waals forces, they exist normally between R chains. So if you have a big R chain, then you have a van der Waals force over here. Now since you have an aldehyde, a CHO is an aldehyde. Since you have an aldehyde, you have a dipole-dipole interaction over there. So with the aldehyde, you have a dipole-dipole interaction. So that aldehyde has two types of forces. It has the van der Waals and it has the dipole-dipole interaction. That alkane has only van der Waals interaction. This is nonpolar. All of this is nonpolar. The aldehyde is polar from the aldehyde part. So as the polarity increases, as the intermolecular force strength increases. So this guy has a van der Waals forces, VDW, van der Waals forces. The aldehyde has van der Waals forces and it has a dipole-dipole. The alcohol, on the other end, it has van der Waals forces. This is polar. It's more polar than the carbonyl. So it has van der Waals forces, it has a dipole-dipole, and it has hydrogen bonding. It has hydrogen bonding. Why it has hydrogen bonding? Because I have an OH. If I place two molecules next to each other, I'm just gonna represent this as an R. So if you have two alcohols next to each other over here, let's see, will they have a hydrogen bonding? Let's see if they satisfy the rule over here. So I have a hydrogen that is connected to an electronegative element, and this hydrogen will bond to an electronegative element. So this is my first hydrogen bonding. My second hydrogen bonding, I have a hydrogen that is connected to an electronegative element, and this one is going to bond with the electronegative element. Put your lone pairs on the oxygen in there. So yes, I have two hydrogen bondings over here. So alcohol undergoes or has a hydrogen bonding. So between the alkane, the aldehyde, and the alcohol is going to be the strongest because it has all three types of intermolecular forces. And then we have an example of the ion-ion. This is between ionic bonds. So sodium chloride, lithium fluoride. These two over here, they have basically an ion-ion interaction. Since they are ionic bond, the type of interaction is between ions. So it's an electrostatic type interaction over there, which is the strongest type of intermolecular force. This is an F minus. An electrostatic type of interaction, stronger type of intermolecular force in there. It's extremely strong, stronger than hydrogen bonding. Now, with respect to the physical properties are determined by the type of intermolecular forces that you have. So the stronger the intermolecular forces, normally the higher is the boiling point. Boiling points, they are affected by the intermolecular forces. So to define the boiling point of a compound, it's the temperature at which the liquid is converted to a gas. And whenever you boil a compound or a solution, normally energy is needed to overcome the attractive forces, because basically what you're doing here, you are breaking bonds. So this is why energy is needed. The stronger the intermolecular forces, the higher normally the boiling point. So this is why if you see compounds having hydrogen bonding versus compounds having dipole-dipole interaction in van der Waals, basically the boiling point will increase as the strength of the intermolecular force increase. So a compound that has an alcohol will have a higher boiling point than that of the aldehyde, than the pentane, because alcohols have van der Waals forces, they do have dipole-dipole, and they have hydrogen bonding. Aldehydes, they have basically dipole-dipole, and they have van der Waals forces. Pentanes is an alkane, so it just has van der Waals forces. That guy is nonpolar. So as the number as the strength, of the intermolecular force increase, as the boiling point increase. Also, surface area plays a very important role in the boiling point. The larger the surface area, but you have to compare basically over here within the same functional group. So here I have a carbonyl, I have a ketone and a ketone over here. I have two types of ketones. So you compare normally within the same type of functional group. Comparing two ketones, this ketone has a larger surface area. So the boiling point is going to be higher. Between these alkyl halides, so notice how I'm comparing. I'm comparing between two groups that basically have the same electronegative. It's not this. It has an electronegative element from the same family. So I am comparing here an alkyl iodide and an alkyl fluoride. Both are electronegative elements. These are halogens. So boiling point will be affected by the size of the halogen. The halogen over here, iodine, is bigger, so the electronic cloud around the iodine will occupy a larger surface area, and the electrons will be loosely held. The valence electrons will be loosely held in this case, and they will occupy a larger surface area compared to the electronic cloud around the fluorine, which is more pushed towards the nucleus, and it occupies a smaller surface area because of the size of the atom. So that is going to make the fluorine less polarizable, and it's going to cause it to have a lower boiling point than that of the iodine. In the lab, normally we can separate two compounds based on their boiling point. There are two types of techniques that normally we use, and we will use those two techniques in the lab. Um, in order to separate compounds based on their boiling points. The first technique is called simple distillation, and the second one distillation, and the second one is called fractional distillation, and the second one is called fractional distillation. What I have in the picture here, if I'm mistaken, if I see correctly there, this is basically a diagram for a simple distillation. You do have your mixture in a round bottom flask. Normally when you separate liquid, this means that you have two liquids in there, and the liquids, they have two different boiling points. The boiling points of these liquids has to be normally far away from each other. So when you want to separate two liquids in this technique, in distillation, one of them should have a lower boiling point than the other. And we prefer that the boiling points basically are not close to each other. So let's say, for example, one is 50 degrees, boils at 50 degrees. Another one should boil probably at 75 or 80 degrees. Then you can easily separate those. The first technique in here with simple distillation, you have your round bottom flask, you put your liquids in it, and then you heat the liquids up. Same thing as the fractional distillation. When the liquid boils, the first component that normally boils at a lower temperature, it's gonna start turning into vapor, and it's basically going to pass through. It's basically vapor. It's gonna pass through a condenser. This is called a condenser. Now the condenser normally is cold because it has water running through it. So it is normally cold. So once the gas goes into the tube or reaches the condenser, the gas is going to condense into a liquid. And when it condenses into a liquid, normally it's going to turn here into a liquid. Once it turns into a liquid over here, you're gonna collect it in this collection vessel. So you start by collecting your low temperature component first, and then after you collect your low temperature component, then you raise the temperature of your heating mantle, and then you allow the second component to evaporate, and then to distill. And this is how you separate components based on their boiling point. Now, normally with simple distillation, it is not accurate. If you have two components in the liquid that are closer in boiling point, normally you cannot easily separate one from the other. So you will have, when you collect one, you will have a little bit of the other in it. So the best way to do it is to do fractional distillation. With the fractional distillation, see that column over here? With this column, this is another condenser. You have two condensers in here. The difference between this condenser, normally this condenser is not connected to the water. With the fractional distillation, normally we stuff this with a large surface area material, like for example copper. So we stuff it with copper, with a copper wire, something like this, in order to increase the surface area of the column. So when the first component starts boiling and it normally turns into a gas, the second component, if it want to boil with it, the second component will basically condense, and it will return back to the distillation flask. It will not be allowed to evaporate until all the first component evaporates and condenses and you collect it. So basically what you do in fractional distillation, you increase the surface area of your condenser so that you provide a better separation between the two components in your mixture. So what type of intermolecular forces are present in each compound? Okay, if you have a CC bond, CH bond, it's going to be van der Waals forces. In this case, so this is going to be nonpolar. This over here, since you have oxygen, then this oxygen over here will introduce a dipole. See, it will introduce a dipole. So you have here a polar CO bonds on both sides. That is going to be partial positive, and this carbon here is going to be partial positive. The oxygen is going to be partial negative. So you have two polar CO bonds. This is a dipole-dipole interaction. You have van der Waals forces because of your carbons over here. You don't have any hydrogen bonding. For the alkyne, just van der Waals forces. For the amine over here, this is this amine there, this is a tertiary amine. So for this amine, what you have here is basically a dipole. See, you do have a dipole in this case. This is going to be your dipole. The CO bond, these are polar CN, I'm sorry, these are the CN bonds. These are polar. You don't have any hydrogen bonding, and you have van der Waals forces because you have carbons. Here you still have van der Waals forces. You do have polar CCl. You do have dipole-dipole, so two types of intermolecular forces. This is your electronegative, so that is going to be partial positive. This is going to be partial negative. The moment you introduce a dipole, then you're going to have a dipole-dipole interaction. With this one, I have van der Waals forces. I have dipole-dipole interaction. I have two oxygens over there. See, CO and CO over there. So I have polar CO bonds. This is a dipole-dipole, and I have hydrogen bonding to the oxygen. Why hydrogen bonding to the oxygen? Because I'm going to label this in R. So you have two acids next to each other. So this is an acid, and then this is another acid. Okay, so the definition here, you need to have a hydrogen connected to an electronegative element, and that hydrogen will bond with an electronegative element. Or here I can have a hydrogen connected to an electronegative element, and that hydrogen will bond to the electronegative element. Or that hydrogen, you know, can bond here to this electronegative element. So I have here two types of hydrogen bonding. So normally all compounds, they have van der Waals forces. Polar compounds, they have dipole-dipole interactions. Hydrogen bondings occur when a hydrogen is connected to an electronegative element, and it basically interacts with an electronegative element. To have a higher molecular boiling point, you need to have a stronger intermolecular force. So ionic forces, these are the strongest type of intermolecular forces, and then you have hydrogen bonding, then dipole-dipole, and then the van der Waal interaction. Also, there are two factors that affect the strength of the van der Waal forces: the surface area and the polarizability. So if I am comparing between these two compounds, this one is a larger molecule or a longer molecule, higher surface area, higher boiling point than this compact molecule here. This has van der Waal force, this has basically hydrogen bonding, it has van der Waal and dipole-dipole, so it has a higher boiling point. The acid, the moment you see an acid, acid undergoes hydrogen bonding. So acid has all types of intermolecular forces, with the exception of the ion-ion. This is an ester. Ester does not have any hydrogen bonding, so this acid is going to have a higher boiling point. Between an alkene and a ketone, both have dipole-dipole interactions, but one of them is polar. Okay, one of them is polar, the other one is not polar. So this guy over here is not polar. This one is going to have a higher boiling point. And now look at the size. Iodine is larger in size. It is more polarizable than the chlorine. Then we have the melting point. By definition, the melting point, it is the temperature at which solids normally are converted to liquids. And the melting point, normally energy is needed to overcome the attractive forces. It's the same thing as the boiling point. The stronger the intermolecular forces, the higher is the melting point. And normally within the same functional group, this is what melting point parts from boiling point. If you have the same functional group, you are looking for a more symmetrical compound to have a higher melting point. With the boiling point, I was looking for the larger surface area. But with the melting point, I don't want the larger surface area. I want a symmetrical compound so that I can get even heating. So the melting point will be higher in that case. If you're looking at a covalent bond that has the same molecular weight, if you're comparing between them, the melting point depends on the functional group and it depends on the type of intermolecular forces. So we're still going to say, as the boiling point, the stronger the intermolecular attractions, the higher is the melting point. What parts the melting point or what differentiates the melting point from the boiling point is that with melting points, I am actually looking for a more symmetrical molecule. If you have a more symmetrical molecule, like a compact molecule like this is called neopentane. This is neopentane. This is another name for neopentane, 2,2-dimethylpropane. This molecule over here normally packs well into a crystalline lattice, whereas the 2-methylbutane, which is isopentane, it does not. It has a larger surface area in here. So this is why the neopentane is going to be higher in melting point. So let's have an example. Which molecule has a higher melting point? Again, the stronger the intermolecular forces, the higher is the melting point. And over here, I didn't write the charges. The moment you see group 1, then it is going to be an ionic bond. Sodium is positive, oxygen is negative. Write your lone pairs. This is basically an ionic interaction. So you have an ionic bond. This is going to be the strongest. So you have higher melting point in this case. compared to the acid. Acid is very, it does have very strong intermolecular forces because it has hydrogen bonding. This structure, the ionic structure, doesn't have hydrogen bonding, but it is an ionic bond. It has an ion-ion interaction instead, which is way stronger than hydrogen bonding. The more compact the molecule is, the more spherical it is, the better it packs in the crystalline lattice, the higher is the melting point compared to this structure. And if you're looking at two compounds, always check the functional group, because if you have a molecule that has a higher or stronger intermolecular forces, then immediately that molecule will have a higher melting point than the other. Another term is the solubility. Now, solubility is dependent on the type of intermolecular forces. What is solubility? It's basically the extent to which the compound, which we call it here a solute, dissolves into a solvent. So it's basically it basically explains how a solute dissolves in a solvent. And in order for a solute to dissolve in a solvent, the energy needed to break up the interaction between the molecules, I mean the solute, because after all the solute is dissolving into the solvent over here. Normally, the energy needed to break up the interactions between the molecules of ions of the solute comes from new interactions between the solute and the solvent. Let me give you an example over here. We know that like dissolves like. So for example, for NaCl, to dissolve in water, the rule for NaCl to dissolve in water, I need the intermolecular forces to basically have the same magnitude for the NaCl to dissolve in water. So this, for this, I should look at the intermolecular forces that are between the sodium chloride, and I should compare these intermolecular forces between the solvent, which here in this case water, and I should look at the intermolecular forces that will form between the sodium chloride and the water. The magnitude of these intermolecular forces has to have the same energy for the sodium chloride to be dissolved in water. So for example, sodium chloride dissolves in water. Water is polar. Sodium chloride is ionic. The reason why sodium chloride dissolves in water, first, because sodium chloride, the intermolecular forces between the sodium chlorides are ion-ion interactions. The intermolecular forces between the solvent is basically hydrogen bonding. The magnitude of the energy of interaction between hydrogen bonding is the same as the ion-ion interaction. And then if you look at the sodium chloride with respect to the water, when sodium chloride dissolves in water, the sodium chloride forms an ion dipole interaction. That ion dipole interaction also has a magnitude which is similar in energy to the ion-ion and the hydrogen bonding. So always like dissolves like. Solutions form when the intermolecular forces involved in the three kinds of interactions are similar. So similar in what? They are similar in energy, similar in magnitude. This is what I mean. So the amount of energy that it takes to form ion-ion interaction is the same as the hydrogen bonding is the same as the ion dipole. And this is why sodium chloride dissolves in water, which is basically polar. So like dissolves like. On the other end, if I have hexane and I have benzene, hexane is nonpolar. Nonpolar hexane dissolves in nonpolar benzene. So hexane is basically a chain of 6 carbons. This is what a hexane is. It's an alkane chain of 6 carbons. 1, 2, 3, 4, 5, 6 over here. So hexane dissolves in nonpolar organic solvent like benzene because benzene has van der Waals forces and hexane has van der Waals forces over there. Okay, so the magnitude of these forces are the same. So when you form a solute-solvent interaction, you are still having van der Waals forces over there. The magnitude of the intermolecular forces is the same. So most ionic compounds normally are soluble in water because like dissolves like. They are insoluble in organic solvents. And same thing whenever you have a nonpolar compound. Nonpolar compounds, they are soluble in nonpolar solvents. And they are soluble in weakly polar solvents. Polar compounds, they are soluble in polar solvents like waters, like alcohol. So let's see over here, since butane and acetone are both organic, normally in the lab we use acetone a lot and we use it as a washing solvent for all organic compounds because acetone can dissolve organic compounds and it can dissolve also polar compounds. It can dissolve polar compounds because it does hydrogen bonding between them and it has a dipole-dipole interaction. So acetone is soluble in water. Acetone can dissolve polar compounds because it has a polar bond. It has a polar CO bond over there. On the other hand, butane is a chain of 4 carbons. Butane is nonpolar. So since butane is nonpolar, it cannot be dissolved in water. Acetone is polar. It can be dissolved in water. That type of solvent, as I said, we use it a lot in the lab as a washing solvent. The size of the organic molecule with the functional group normally depends or affects the solubility. For compounds to be soluble in water, they shouldn't have more than 5 carbons. So 2 carbons here, then and I have a polar bond, then basically ethanol is soluble in water. The polar bond is basically is a must, but it's not enough for the compound to dissolve in water. For a compound to dissolve in water, it should have 2 things. It should have a polar bond and it should have no more 5 to 6 carbons. This is the max. So if you look at cholesterol, it does have a polar bond, but it has a lot of auto groups in there in forms of cycles, so it's the carbon skeleton is pretty much large, so there is no way for cholesterol to be soluble in water. So as a rule, alkanes are insoluble in water. For alcohols to be soluble in water, they should have less than or equal to 5 carbons. If you have more than that, then your compound is not going to be soluble in water. If the compound normally is insoluble in water, then immediately it's going to be soluble in organic solvents. Let's predict the water solubility. You have 2 types of vitamins, vitamin K1, vitamin B3. Again, you should have a polar bond and the chain or the number of carbons in your structure. Now, since this is a cycle over here, it has 1, 2, 3, 4, and 5. Let's see, 1, 2, 3, 4, and 5. So it has 5 carbons. This is 5. It has 5 carbons over there. Again, this is 5 carbons in the cycle. And then 1 more carbon. So that 1 more carbon, it is basically a substituent on the cycle. So you just count the carbons of the cycle and the carbons of the cycle are 5. So that satisfies the rule that we said that you need to have not more than 5 carbons for the molecule to be soluble. So this is soluble in water. It does have two polar bonds, see? It does have a nitrogen, which is polar over here. So the compound is soluble. For vitamin K1, although it has the two polar bonds, the CO bond and the CO bond, these are two polar bonds, but the rest of the chain is nonpolar. This is a nonpolar long hydrocarbon chain. That hydrocarbon chain doesn't like water at all. It repels water, so we call it hydrophobic. This is why the molecule, the whole molecule, is not going to be soluble, water soluble. Remember that likes dissolves like. To be soluble in water, molecule has to be ionic or should have a polar functional group. That polar functional group has to be capable of hydrogen bonding for every 5 carbons. So it should do hydrogen bonding for every 5 carbons. With respect to the organic compounds, normally they are soluble in organic solvents regardless the size of the functional group. So we don't care about how many carbons we have in the structure once we look for organic compounds, because immediately these organic compounds will be soluble in organic solvents. Examples of organic solvents like, for example, carbon tetrachloride, CCl4, that we use this a lot, chloroform, CCH3, we use that too. So this is a chloroform. This is carbon tetrachloride. And you have acetone. This is another organic solvent that we use. I'm labeling this as an organic solvent. It is not water-based. This is an organic solvent, but it can dissolve in water because it can do hydrogen bonding with water. The last topic in this chapter is the functional groups and the reactivity of the functional groups. We said that functional groups are reactive sites. So if they are reactive sites, normally they induce a dipole. So from the functional group, you can easily determine where is your electrophile and where is your nucleophile in that case. If you have an oxygen functional group, that is going to be your nucleophile. If you have a nitrogen functional group, this is your nucleophile. If you have a pi bond functional groups, again, these are all nucleophiles. Nucleophiles react with electrophiles by a Lewis acid, Lewis base reaction. If you have a nucleophile that reacts with the alkyl halide, this is partial positive, then your arrow is going to be from the nucleophile towards the carbon of the alkyl halide. If I look at the butane, butane is soluble in organic solvents. Butane has van der Waals forces. Water has hydrogen bonding. The magnitude of the intermolecular forces of the van der Waals compared to the hydrogen bonding is not the same. So this is why butane cannot be dissolved in water. It is insoluble. There is no sort of interaction between them. Acetone on the other end, acetone over here can do hydrogen bonding with water. So acetone is soluble in aqueous solutions. Aqueous solutions, these are solutions that are water-based. Organic solutions are solutions that are organic-based. Carbon tetrachloride is nonpolar. Carbon tetrachloride is nonpolar over here. Acetone has a dipole-dipole interaction, and it has nonpolar groups. This is this carbon over here and this carbon over here. They are nonpolar. So acetone will be soluble in organic solvents because of the nonpolar part of the molecule. Okay. For the soap structure, soaps, these are molecules. They have two distinct parts. They have a normally soap molecules, these are salts of carboxylic acids. So if you have a carboxylic acid and the carboxylic acid loses its hydrogen, so this is the carboxylic acid. If the carboxylic acid loses its hydrogen, becomes a conjugate base, then the carboxylic acid will become a salt. So this is what we call a salt. Okay, so soap molecules should have a salt head, which is the conjugate base of the carboxylic acid. The salt head normally is the polar head. It's the polar head because the type of interactions between the ions, this is an ion-ion interaction. And then it should have a nonpolar tail. The nonpolar tail is the long carbonate chain. Normally, the long carbonate chain, which is the nonpolar tail, this is hydrophobic. It doesn't like water at all. So this is why when soap is in contact with water, it arranges as a micelle. What is this? A micelle is the type of arrangement that the soap molecule undergoes, where its polar head normally faces the water and its nonpolar tail stays always away from the water. So it forms like a bubble, like a ball. It forms like a ball just to make sure that its nonpolar tail always stay away from the water. And this is how cleans soap cleans by basically making sure that its nonpolar tail stays away from the water. Now its polar head is the one that is gonna face water and do the cleaning. Okay, so we've done that. Let's have an example over here. Which of the following structures represent soap? To have soap, you should have a long R chain. If you have a short R chain, then this is not a soap. A soap should have a long R chain and it should have a polar head. It should have a polar head that is basically the salt of the acid. Here I do have the salt of the acid. I have the O negative, I have the Na plus there. So I do have the polar head, but I don't have the R chain, so this is not a soap molecule. I do have my R chain, my long R chain, but this is not a salt, it is an acid. So this is again not a soap molecule. Now here I do have a long R chain. I do have my salt. This is a negative, this is a positive, this is the salt of the acid. So yes, this is a soap molecule. Okay, so pretty much. So let's have an example over here. Okay, so let's have an example over here. Label the electrophile and the nucleophile sites in each of the molecules. You have to look at your functional group over there. So label your functional group. This is the ether. This is my polar bond. It induces a dipole. So I am going to have two partial positive carbons. I'm going to have two partial positive carbons over here. This oxygen is partial negative. The partial positives, they represent the electrophile. Okay. The partial negative, they represent the nucleophile. So I have here one nucleophile and two electrophiles. This carbon is directly connected to the bromine. Bromine is more electronegative, so this is going to be my electrophile. This is going to be my nucleophile. These two carbons are going to be my electrophile. This oxygen is going to be my nucleophile. This carbon over here is going to be my electrophile. This oxygen is going to be my nucleophile. Please label your lone pairs. This nitrogen is going to be my nucleophile over here. This is partial negative because it's more electronegative than the carbon. And this carbon is going to be my electrophile over there. This is my polar bond. So this is my partial positive. This is my partial negative. This oxygen here is my nucleophile. This carbon is my electrophile. Also, I have another oxygen here, which is a nucleophile. This is partial negative. And this carbon here is going to be my partial positive. This sulfur over here is going to induce a dipole on these two carbons, making each one of them an electrophile. It will become a nucleophile, and the double bond is a nucleophile. A carbon with a negative charge means it has a lone pair, so this is a nucleophile. This carbon over here normally induces a dipole, so the oxygen is going to be a nucleophile, and this carbon is going to be, the carbon of the carbonyl will be partial positive, which is an electrophile. Double bond is a nucleophile. So for the nucleophiles, I have this oxygen here. This is a nucleophile. This is partial negative. This carbon is my electrophile. This oxygen here is my nucleophile. This hydrogen is my electrophile. It is partial positive. This is an acidic hydrogen. Oxygen withdraws electrons or takes electrons away from this hydrogen, makes it partial positive. And you do have here the oxygen. This is a nucleophile. This carbon is partial positive. It is an electrophile over there, and this hydrogen is an electrophile. It is partial positive. This is the end of the chapter. Please try to solve your assignments and let me know if you have any questions.